Now let me focus on a specific aspect of writing high-performance kernel code. At a high level, GPU programming looks like this. There's a bunch of data sitting in global memory, and you have an algorithm that you want to run on that data. That algorithm will get executed by threads running on SMs, and for various reasons, you might want to stage the data through shared memory. Now you've seen for yourself that loading or storing global memory into shared memory or into the local variables of the threads can be complicated if you're striving for really high performance. Think about problem set 2, where you loaded an image tile into shared memory and also had to load a halo of extra cells around the image tile in order to account for the width of the blur. And this can be tricky because the number of threads that want to perform a computation on the pixels in that tile is naturally a different number than the number of threads you would launch if your goal was simply to load the pixels in the tile as well as the pixels outside of the tile. Or think about the tiled transpose example in Unit 5, where we staged through shared memory in order to pay careful attention to coalescing global memory. Think about our discussion of Little's law and the trade-offs that we went over between latency, bandwidth, occupancy, the number of threads, and the transaction size per thread. Remember that we saw graphs that looked sort of like this, where the bandwidth that we achieved as we increased the number of threads was higher if we were able to access 4 floating point values in a single load versus 2 floating point values in a single load versus a single floating point value in a load. Finally, there are ninja level optimizations we haven't even talked about in this class, like using the Kepler LDG intrinsic. In short, Cuda's explicit use of user-managed shared memory enables predictable high performance. In contrast, the hardware-managed caches that you find on CPUs can result in unpredictable performance, especially when you have many multiple threads sharing the same cache and they're interfering with each other. So that's an advantage of explicit shared memory. But that advantage comes at the cost of an additional burden on the programmer, who has to explicitly manage the movement of data in and out from global memory. And this is a big part of where CUB comes in. CUB puts an abstraction around the algorithm and its memory access pattern, and deals opaquely with the movement of data from global memory, possibly through shared memory, into the actual local variables of the threads. I want to mention another programming power tool called Cuda Dma that focuses specifically around the movement of data from global into shared memory.